Welcome and thanks for watching. This is the first in a series of web security puzzles. I'm using these puzzles to explain language tweaks that might help developers write more secure programs. By the way, there are links in the notes if you want to run the code in your browser and play with it. Here's a simple JavaScript program. It has a table with some capital cities for US states and Canadian provinces. This function looks up an entry in that table. The table is mostly static, but Alabama's capital has changed. So this code returns the capital given the year. Here, if the capital is a function, it passes the year. I'd like to contrast this program with one in a more static language. Here's a version of the same program in Go. There's a link in the notes to the Go playground if you want to play around with it in your browser. If I rearrange the white space, you can see that the difference between the two is pretty small. The bulk of the difference is Go's extra type syntax and some module boilerplate. I'm going to try to accurately describe what each version does, and I'm going to be super pedantic to make a larger point. For Go, it's straightforward. Capital of takes two abbreviations and a year and returns the name of the capital. But if I ask for an invalid state, I get a special value. So I'm going to document that. The answer is unknown, returns a special value, nil. Capitals are up to date as of January 2017. There aren't any other corner cases for Go. I wrote a simple function and I found a simple description of its behavior. How well does this description work for the JavaScript version? Since JavaScript coerces values, there are more corner cases. If year is not a number or a 4-digit decimal string, you might get back the wrong capital. Here, the JavaScript code uses the country to find the state table, but the country table is an object with its own prototype. What happens when I look up a property on the prototype? I need to document that. If the country is constructor and the state is name, returns capital O object. And what happens if both of them are constructor? It returns undefined. That's a little odd. Like the Go version, it explicitly returns the special value nil at the bottom, but here I'm getting the special value undefined. If you haven't played around in the CodePen yet, this would be a good time to pause the video and follow the link in the notes. Figuring out why this happens might suggest some security problems. The previous result gave you a hint. In JavaScript, capital F function takes a string and parses it as a JavaScript function. The next time through the loop, it calls the created function. Can I use this to actually execute code? So I'm going to pass for year, I'm going to pass the string alert1. And an alert pops up. Better document that behavior. Country and state are both constructor. It compiles the string value of year as a JavaScript function body in the global scope, executes it, and returns any result it returns. My description of this function now has to include, by reference, a large chunk of the JavaScript language specification. For the Go code, there's a simple, straightforward description of capital O's behavior. For the JavaScript code, there is no simple, straightforward description of its behavior. Worse, an attacker who controls the inputs to this seemingly simple JavaScript program can run arbitrary code, even though the code never mentions eval or function. Many skilled code reviewers wouldn't notice this. If there's any way an attacker can cause two property accesses followed by two function calls with keys and arguments they control, then they can execute arbitrary code. These two property accesses and function calls need not happen in the same function, so local code review won't catch all vulnerabilities like this. I presented this problem to two mailing lists, one for Google engineers who write a lot of JavaScript, and one for web security professionals. They knew ahead of time that they were looking at a web security puzzle, and reported spending more time on this than routine code reviews. Even so, only slightly more than half realized there was a problem. 25% said they saw no need for concern at all, and about a third of reviewers came up with a concrete reason for a rewrite. Here are some of their comments. This person noted that problems were not obvious. This one saw it and thought that in a routine review they would continue on without another thought. And this person came up with a concrete way to make the code better, which is great. The problem here is that the capitals table looks like it's just about capital cities, but in JavaScript, square brackets don't just return info about capitals, they also return information about the type used to represent the table. This is relevant to security because of another quirk. In JavaScript, big F function is also overloaded to turn a string into runnable code. This is a contrived example, but it illustrates a general problem. Widely used features of the language, square brackets and functions as values in this case, have complex meanings that can combine in subtle ways to break security. Some saw this and suggested better linters and type systems. These are great tools, but they do not address this problem. ESLint does not flag anything in this code as a security issue. If you translate this program to TypeScript, it has the same problem because TypeScript compiles it to equivalent JavaScript. TypeScript does warn if you try to pass a string in for year. That's great, but TypeScript also allows unchecked casts, so we still cannot rely on year being a number. Even if we shut off specific problems like capital F function, the problem remains that simple code does not have a simple contract. Designed by contracting code reviews are not sufficient to produce secure programs. I'm a security engineer. I work to make it easier to produce secure software. We have more experience explaining what it takes for something like the Go code snippet I showed to be secure. I love JavaScript though, and I'm trying to find better ways to come up with security stories for dynamic systems. We need ways to limit the damage when code doesn't meet its contract. We security engineers have gone as far as we can with unassisted review and unsound tools. In the next few videos, I'm going to present more security puzzles and their consequences for security in dynamic systems. Later, I hope to convince you that two simple mechanisms would allow small amounts of carefully crafted code to uphold its contract, regardless of the actual behavior of the vast majority of code. I hope to also convince you that this is sufficient for many important security stories. If you're worried about this kind of thing in your code, Content Security Policy can help you on the browser side. On the Node.js side, the disallow code generation from strings flag will do the same. These are the best options available today. Thanks for watching.